think I'm live. I think I'm live. And we are live. Let's give it a moment. Maybe two more people show up, and then whatever. But hi everyone. My name is Zach, and I'm an open source software developer who's trying to really get familiar with building his own hardware. And the way I've chosen how to do this is by walking through this hands-on FPGA class that was given by Venkat Rangan a few years ago. This belongs to the Tiny Vision AI consultancy. You can find them on tinyvision.ai. And today we're going to be covering the material for week 3. Just the material, and then I think we'll start working on the exercises from tomorrow. Yeah, that's kind of what we're going to be covering today. And the way I'm going to do this is so that it's some sort of little exploration, and we can walk through this information that is shared here, and we can kind of reason out why this information is sort of important or not. So there is a slide deck that we're going to be using. I think it's on here. There's a slide deck that we're going to be going through, and then after the slide deck, there's a couple more links and information that we can follow through. So let's get set up, and then let's get going. Cool. So do I want to close this? Maybe this is much better. So hands-on with FPGAs module 3. That's what we're going to be covering through today. And the main thing that we're going to cover today is clocks. Clocks are weird. Clocks are important. Clocks are sort of like very key, because when you almost can't do anything without clocks. And it's very easy to mess up your clocks, or to be out of sync or in sync with your clocks. So let's look at some basics. Let's cover some clocks, and then we can go forward from there. There's a bit of noise outside, so I'm kind of pausing a bit before the noise goes away, so that I start when the noise is gone. Feel free to say hi. Feel free to leave a comment. The description of the video has a link to our Discord community. You can join us, and you can hang out with us, and we can walk through stuff and whatever. Anyways, so this is a module that was made by Venkat Rangan. He's a professor, or rather, he's a professor, or used to be a professor at the University of San Diego, and then he's an ACM fellow. He's very accomplished. He's got like something like 40 or more than that patents to his name and such. Cool. So let's look at this. So what we're going to cover today is clocks. What is a clock? Why do we need a clock? Interesting things about clocks and how to use clocks. Additionally to that, we're going to cover resets. What are resets? Why do we need resets? And sort of types of reset. And we might look at some verilog at some point. We might not. It all depends on kind of how this goes. Okay, cool. So let's look at this. Clocks and digital circuits. So what are digital circuits? Is sort of like what we're building on the FPGAs. We're building little integrated circuits, and these integrated circuits are supposed to do some tasks at some point. Immediately in that statement, we start seeing what clocks are and why we need them. We're building integrated circuits, and these integrated circuits need to do some sort of tasks at some sort of points. In order for the circuits that we build to determine which points they're going to need to do what task, they need to know at what point they are. It's like a little concept like whenever I say that sentence, I always think about dead reckoning. It's kind of like finding out, is it what is dead reckoning? Is it finding out what is dead reckoning? Dead reckoning definition. What is dead reckoning? Dead reckoning is the process of calculating the current position of a moving object by using a previously determined position. So this is sort of like finding out, I would say this is finding out where we are based on where we were, and also finding out where we're going based on where we were and where we are right now. So the same thing with clocks. In order for the integrated circuit to determine what time it is, it needs to know what time it was and what time it's going to be, and then that way it knows what time it is. And this goes this goes into like Aristotle's thing. Aristotle on time. Aristotle says time is not a thing because time divides what was, which no longer is, so a nothing, and what will be, which is not yet, so a nothing. But time now cannot be the same always. So in a way, time is nothing. Time is a border made of nothing, between nothing and nothing. That's one of like Aristotle's like beginning riddles, which he never answers himself. So we don't know what we can't really say. So the time is a particular position in like, forgive me for using terms that I might not understand, is the space-time continuum. So it's the now that is separating that was and that will be. That is kind of what time is. Okay, cool. And we use clocks to sort of determine positions. Like we use clocks to sort of determine how much time has elapsed, and how much time has elapsed are things that help us. How much time has elapsed helps us determine what needs to be done and when it needs to be done. So if you give let's think about the quintessential what is this? The quintessential I'm blocking blinky example. You have a blinky. You have an FPGA. You have an FPGA, which we can quickly do actually. So let's go into UPduino. Let's go into UPduino RTL here, and let's copy a module and let's make blink LED. Yeah, let's make this one RGB blink. This one. Let's copy this one, and then I think we actually already have it. Why do I feel like we already have it? Ghosty. Why do I feel like we already have it? See, documents, eng, ls, RTL digicom. Yeah, I think we already have it. CD RTL digicom. I think, and then this should be a blinky, and this should actually be able to show us what time is. Perfect. Let me quickly build that and deploy that basically. That should actually go. Amazing. And then if I go like up your build, it should build a thing for us quickly. And then if I go like iceprog into build default hardware bin. And you can see here, that's basically what we're building. It's a blinking. It's running through the red, green, and blue LEDs, and it is blinking red, green, blue, or red, blue, green, whatever pattern it's going through, it's blinking that. And this actually gives us a good example of what is time. So time is the period between the blinks. Okay, and then what is a clock? A clock is the thing that we use to determine how much time to wait before blinking the next color. So we need to know when the last color blinked, so that we know how much time to wait before blinking the next color, and so on and so forth. And basically, that sort of gives us a little introduction at what you know time is. Time, time and clocks. Now we're in clocks. So time and clocks. What a clock is. Um, and as is explained here, clocks are one way for circuits to have memory. So if I know what time it was, then I know what time it is now, and then I keep checking how long it has passed since the time it was. Then I will know I've hit a certain barrier. I should now do something else. Clocks are basically built up of a flip-flop register. Basically, specifically a data flip-flop register or a D flip-flop register. And a D flip-flop register is a more stable version of an SR latch. I wonder if this link will open for us. Oh, I can do that. Open hyperlink. Let's go look at this. Yeah. Okay, good. So let's view. So this would sort of be something that there's a. I apologize. There's noise outside. So this is something that has an SR latch, and this is going to be. I think we can probably run it probably or something. Yeah. So you see, it has stability issues, but that's okay. That's okay. And then here, if we go clock. So clock 1, data 1, clock 0, data 1, clock 0. Okay, wait. So data, level sensitive latch. So let's see. SR latch 1. If you set, it lights a green. If you remove the set, the green goes off. If you reset, it lights a red. If you remove the reset, let's see that. If you remove the reset while the set is 0, then the red one goes off. And what if this one is not set? What if this is set? This never occurs. This never passes. So this is set, it's set. Okay, and then here we have a data. Let's set it. Let's set this data bit, and then we wanna toggle the clock. We get a green LED. We untoggle the clock. So it depends on the data changing again. Basically, what we're trying to show here, is that these two circuit blocks, these two digital logic blocks, are the ones that form the basis of clocks. This is how clocks are made. Clocks are basically made using D flip-flops, and D flip-flops, data flip-flop, D flip-flop. I already had one. D flip-flop. I already had one. So D flip-flop. This forms the basis of, a flip-flop, and latches are circuits that have two stable states and that can store state information, a bistable multivibrator. The circuit can be made to change states by signals applied to one or more control inputs, and will output its state, often along with its logical complement. It is the basic storage element in sequential logic. So this flip-flops give us the base. Flip-flops and SR latches, or rather flip-flops and latches themselves, give us the basic elements that we need in order to have memory in integrated circuits. Basically, that's what's being said here. And so D flip-flops form the basis of most digital logic circuits. And a digital heartbeat is a synchronization between different parts of a design. Every circuit knows when it's time to do something. So this is the same thing that is happening here. This is the same thing that is happening in this verilog if you look at it. So we have an LED, we have a circuit, we have a little circuit that does the green LED and the LED and the blue LED and the green and the red LED. And then we have another circuit that actually implements an oscillating clock. So this is an oscillator, like a crystal oscillator, and it implements this up down logic every so on and every so often. And what happens here is that I think we do at some point we do some sort of no, this is set when B1 this is set when it's 24. Okay, 25 and 24 and 24 and 24 25. No, this is not, this is, why are they all set at the same time? 25 24 25 24. Let's set this one at not 25 and 24, but rather let's set it at 23 and 24, and then let's set this one at 22 and 23. I think so. This is some sort of this in itself is some sort of digital heartbeat. This in itself is some sort of digital heartbeat. Wait, let's go 25 and 24. Let's go 23 and 22, 22, 23 and 22. And then let's go 23 and 22. And then let's go 20 and 21. What am I trying to do? I'm trying to make them all distinct. I'm trying to make them all distinct. Look at what is happening right now. Look at what is happening right now. This is actually quite a nice observation. Let's look at it. This is quite a nice observation. So they're going like red, blue, green, red, blue, green, red, blue, green, and it's quite fast and it's quite followed. I think this one might enable us to give us a gap or something. Let's actually look at what happens when we do this, and what we're showing here is a digital output, which is basically synchronization. There's a bunch of circuits that are agreeing to do things based on another digital circuit by itself. So there is a clock that is counting how many bits, that is filling in bits. That is because remember, we declare a 28-bit register here, and then as this 28-bit register here goes on, this is a binary counter here. This is a binary counter, and a binary as we did yesterday. Remember when we were doing the other module yesterday? The binary counter, you count from the right to the left. And my hands might be opposite because of the video, but you count from the right to the left. And then what happens is whenever you get to a 1, you reset the 1, it goes to 0, and then the 1 next to it is set, and then you go to a 1 again, and then both are 1s. And then when you get to the limit of the little box that you're in, if you have 3 bits, you get to the limit, it's 1 1 1. You roll over to the next. You add 1, roll over, add 1, roll over, add 1, roll over. So what is happening here is we're telling this circuit to light up RGBO when bit 25 and bit 24 are set, and then we also want it to be RGB1 when 22 and 23 are set, and when 20 and 21 are set. Actually, let's use an excalibur. Let's use an excalibur. Let's use some sort of excalibur here. We'll get to this one later. So let's actually draw a box here. Box. Let's actually draw a box, and then let's give it a few divisions. Like, we don't have to do that many. We don't have to do that many. We can do just how many? How many is this? 1, So what happens? This is what happens. On run one, this is 0, 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 and then this is 0. This is on clock pulse 1. And then on clock pulse 2, this becomes 1, this is still 0, this is still 0, this is still 0, this is still 0, this is 0. And then on clock pulse 3, what happens? So this is 1, this will roll over, and then this one will be added. So this is 0, it will roll over, and then this one will be added, and then this is 0, and then this is 0, and then this is 0, and then this is 0. And then on the next clock pulse, what happens? This becomes a 1, this is stays a 1, and then this is 0, 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 and then and so on and so forth. So this is rolled 0, 1, and then wait 1 0 1 1, and then this is now actually going to get rolled over. So this is going to be a 0 again, and then this is rolled over, and then this is 0, and then this is 0, and then this is 0, and then this is 0. We're doing a binary counter by hand. And then this becomes a 1, this stays a 0, this stays a 1, this stays a 0, this stays a 0, this stays a 0, this stays a 0, and so on and so forth. So what we're doing here, what we're doing in this code, what we're actually doing in this code is we're telling the RGB driver to wait until the 24th, when the 24th and the 25th bits are set. So if this was going through, if this was 24th and 25th, when the 24th and the 25th bits are set, actually light that thing. You see, because this is an AND here. Okay, and this is going AND not. Oh, actually, yeah. So let me just make this an AND, and let me remove this a not. This not. And then we just let's set it at this and see what actually happens. Happy build. So this is the current pattern that's there. Okay, it might not even look that different, by the way, or it might even not work. Okay, see now it's changing. It's changing quite a lot. Okay, see, amazing. And then so that's a really interesting one. And then we can go like this is a not here. So when it's not 22 and it is 23, and maybe when it is not when it is not 21 and it is that. Let's see what happens. So what are we doing? We're doing up a build. This is a current one. This is a current one, and then we'll actually do an upload. Let's see how it changes. It's gonna be as fast as the other one. It's gonna be different. Yeah, something different. The other. Ooh, yeah, I like it. It rushes, it stabilizes. It rushes, it stabilizes. We can also go like instead of these knots, how do you make like a predictable one? How do you make a reliably different one that actually looks different? You can always use the same bits, or you can use super far away bits. Like we can go like this is 1 and 1 and 24, 1 and 14, cool. And then we can go like this is like so let's go a bit more. This is like 8 and 23 is fine. And then this one can also be this can be 16, and how many bits is this? 27. So 16 and 26. I don't know if this will be reliably different. I don't know if we'll be able to spot a difference as humans, but let's see. Nice build. Nice pro. Ooh, yeah. Nice. You can see a difference. So what are we doing here? We've made a heartbeat. We've made a central. Let me see if there's any questions or anyone. What we've done here is we've made a central sort of. What do we call it? A central sort of signal, and then there's this central signal that is controlling this. We have a central signal here. We have a central signal here in the. We have a clock. We have we have an oscillator, and this oscillator is a silicon blue high frequency oscillator. I don't remember how much it's running at. I don't remember how much it's running at. SBHF OSC frequency. I don't remember how much it's running at, but like, yeah, it's running at 48 megahertz. So we have a clock that is running at 48 megahertz. So every 48 million times a second, 48 million times a second, this counter, this 28-bit counter is incremented. Whenever that counter is incremented, it's of a certain value, and that value is then used by this RGB LED driver to determine the values of this actual LEDs that we have. So it goes like, is this in this set, 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 and what results there, what happens there, what we get in the end is we've made a heartbeat that synchronizes some sort of, there's this agreement that is going on. There's this agreement that is going on that is causing our circuit to agree in certain states and agree to do something in certain states. And this is called sort of what clocks are really good at this. Okay, when something happens, when X happens, do Y and Z. When Y happens, do X and Y. When you know, so, and so on and so forth. So every circuit knows when it's time to do something because of clocks, and it can agree on doing a lot of things because of, like, as you can see here, it can agree on doing a lot of things because of a clock. So because the clock tells it what time it is, and then it goes on to do whatever it needs to do. Okay, so let's go to the next one. Properties of a clock. We need to know the frequency of a clock, which is sort of that frequency of a clock, and then there you go. Actually, this is really good. This is on ice prime, so that's fine. Yeah, this is sort of what we want to know about a clock. And can I copy this? Copy, and where can I put it somewhere so that we can see it? If I do this, yeah. Okay, cool. No. So we need to know the properties of a clock, which is the frequency. What frequency is it oscillating at? We need to know the duty cycle of the clock. How long does it stay on, and how long does it stay off? And then we need to know, so we can find this out. So what is clock frequency? This is how many times it oscillates per second. It's measured in hertz usually. Okay. So clock rate or clock speed in computing typically refers to the frequency at which the clock generator of a processor can generate pulses, and is used to synchronize the operations of its components. That's kind of that thing. And then duty cycle is how long it stays in the low versus high. You know, this is how long a signal stays. Yeah, here you go. You can see it here. So there's a 100% is it staying fully on. 10% is it's only 1 out of 10, and then 20% 2 it's on, 8 it's off, 50% 5 it's on, 5 it's off, and so on and so forth. So we need to know these properties of clocks. These are the properties of clocks that we need to know. I think the next one we wanted to know is clock jitter. So this is how long it kind of like it shakes. It's not the best. This is the how long does it like kind of vibrate? Because we're talking about crystals, we're talking about systems that change, we're talking about signals in the real world. they're not always the same. They're not always the same. So do they ever variate? Do they ever move? Do they ever like, does it go like how does it sometimes go to a 20 and then it comes back and then start? And so let's read this. Jitter is a deviation from true periodicity of a presumably periodic signal, often in relation to a clock signal. In clock recovery applications, it's called timing jitter, and jitter is a significant and usually undesired factor in the design of almost all communication links. So like I said, this is not something you want, but it's something you have to account for. Will my design actually deviate from the signal, from the frequency that I've set it? And if it does deviate from that signal, by how much does it deviate? And how can I build my design, or how can I build my code, or how can I build my circuit so that I actually work around this jitter period or jitter thing that we have? Okay. So jitter period is the interval between two times of maximum effect and minimum effect of a signal characteristics that varies regularly with time. Jitter frequency, or more commonly known, is the more commonly quoted figure. It is its inverse. Okay, so the period is like, you can go like every 5 minutes my clock will go like 1 second too much, 1 second too late, and then it will go 1 second too early and then 1 second too late. Is the leap year an example of a jitter? Because yeah, so something like is the leap period jitter period? Oh my word. I'm so impressed that I remember that. So this system has less periodic deviation or jitter from its mean than the Gregorian calendar. So we actually are quite familiar with what a jitter is. So this is the thing that causes leap years, because we have a huge clock out there, which is a calendar, and the calendar we have can deviate from the periodicity that it's supposed to do. A year is supposed to have 365 days, and whenever a year has a little bit less or a little bit more of than 365 days, that's called a jitter. That is a jitter period. That is how much the clock, the calendar, is deviating from itself. There you go. So you can relate to jitters like that as such. Okay, so let's go to the next thing. So setup and hold is the time it takes to get to a stable point. You operate the clock. You supply some power. You supply some signals. You supply some crystals. Setup and hold is when it's now ready. Setup is the time it takes to get to the place where it's ready, and then hold is a bit. I think it's a little bit of a padding of that. And then max frequency of an operation is how long it will take, how many frequencies of those frequencies of the operation of the clock frequency, how many of those will it take for some sort of effect? If you change it, if you apply a divider, if you set it up, if you hold it, whatever, how long will that take to get there? Wait, maybe I should Google this so that we just make sure we're good. Set up and hold. Set up and hold. What is set up and hold time? The setup and hold time is a timing condition on a source asynchronous interface with respect to the incoming clock. Nanland actually explains time really well. Setup and hold time are important concepts to understand for every digital designer. This article explains why. So the you see, there's a time that it takes to actually get the clock to where you want it to be. Setup time is the amount of time required for the input to a flip-flop to be stable before a clock age. Hold time is the minimum amount of time required for the input to a flip-flop to be stable after a clock age. So these are all this little minutiae, like little details that you need, especially when you're working on FPGAs, when you're working on this super fast like signals. All these little things become really, really important because you now need to like, you need to like handle them at a very, very fast rate. Because this is hardware. Like sometimes you're dealing with things that are t equals 0. Like it's happened. It happens. It's happened then. And when you're dealing with that, you need to know all these little things because you need to account for them so that you can design actually good circuits. Okay, cool. So let's go to the next slide. Clocks in Verilog. So we've learned this before. We saw this when we were testing the module yesterday. There is no calling the module. Everything runs in parallel. We have a parallel execution. And this is not like code where something happens in sequence, although you can do that. You can make things happen in sequence by using sequential blocks, things like assign, things like initial, things like always, things like initial, things like function, I think things like let. There's a few keywords that will give you sequential operation. All changes usually happen on the positive edge, and we can see this here on a CPU I wrote a little while ago. Tiny RISC CPU. So when I wrote, what you can see here is always on the positive edge of the clock begin, and then the counter changes. We actually don't even have to go there. Here we see always on the positive edge of the int oscillator. Int oscillator is the wire, and this wire is connected to the output of a high frequency clock. So whenever it goes up, and I think this was here. This is the positive edge. This is the negative edge. You can do stuff on the positive edge, or you can do stuff on the falling edge, and you can do stuff on both. You can do stuff on both when you're doing something called double data rate. So you're using one clock pulse for two things, and that gives you a double data rate. If you've heard of DDR memory or DDR RAM, this is sort of the thing they're talking about. There's operations that are happening at the rising edge, and the operations that are happening at the falling edge. And MIPI also works in the same way. If you are around to see the MIPI stream a few weeks ago, MIPI also happens to work on the same in the same concept. Cool. So let's go to the next part. Let's go to the next part of this study series. Between clock edges, signals propagate between registers. So there's these things. There's these operations that are happening. You see these operations that are happening. Okay. There's this. This is probably going to be in positive edge, and then this is going to happen. These are all blocking assigns. I didn't use. If actually we can use at the. We can look at the CPU again. In the CPU, you can see. So there's stuff that is happening after when the positive edge goes, and then there's stuff that is happening here. All of these things are commanded to be happening on the positive edge, but then between the positive edge, all of this data is being moved in between registers and things of the sort, and all of these operations are being performed. And so because of that, whenever you do set something, these are all documents linked on here. So this is this document. I haven't opened this one. This video is you can look at it by yourself, but it's a Sean Heimel video. This is the one. Introduction to FPGA Part 4, Clocks and Procedural Assignments. So this document, you can see here, I want to show you, what is it that I want to show you? signals propagate between registers. So you can see here, uh, it says, whenever you set something, it will be ready the next at the next no, this is lesson 1, sorry, until lesson 2. It will be this, the next time the clock edge is hit, this is when you'll be able to get this data. So basically what happens is that you run an operation here, you run an operation on this rising edge, and then during this stable edge over here, or during this stable edge if you did it on a falling edge, during this stable edge and during this stable edge, data is now propagated between all the registers and everywhere else. So if A needed to be C, A is copied to C. If C needed to be D, C is copied from D, and all of the, and so on and so forth, and so on and so forth. Basically, that's what happens. So between clock edges, signals propagate between registers. Registers are things that have memory. Okay, now this is also another part. So you can do clock sources. Clock sources are just things that give you a pulse. There's a few ways to get clock sources. One way we've looked at, one of the ways we've looked at is we're looking at this code that is written here, and it uses a silicon blue, being hardened IP on the Arduino, or rather on the lattice ICE40, which means there's some silicon that is, I'm sorry, the silicon that I'm talking about and the silicon blue are not necessarily related, but there is a part of the hardware that is dedicated to being a clock on the ICE40 FPGA, and this comes from the silicon blue people who used to make the ICE40 before Lattice bought the ICE40. So that could be a clock source. There's a circuit in there. It's probably made up of a latch and a D flip-flop that gives you a clock signal at a certain rate, 48 megahertz. And then on the UPduino itself, if I could show this, on the UPduino, there happens to be an oscillator. And the oscillator on the UPduino, I think we can look at assets, probably not assets. We can look at board, and we can look at version 3.01, and then I want to open this PDF, which I could have opened from my computer. I think it's going to be here. 3.01, that's the one we have, and then there should be this PDF. What I want to show here is that there is a 12 megahertz oscillator. This one. It's provided as a part of the hardware. Oh, I wish I could find the part number. There should be a part number here. I don't know if it's this one. But there is an oscillator. It's a hard oscillator. So you get a hard oscillator with this board, and that can be used as a clock source. You can also implement one of the other ways you can do is you can implement a button, and you can be your own clock, and you can press the button and send a signal at whatever rate. You can look at the time and go like, it's been 5 minutes, press the button, it's been 5 minutes, press the button. You can provide a signal that acts as a clock, basically is what I'm saying. And then you can use a quartz oscillator, you can use an RC oscillator, which is a resistor capacitor oscillator, or you can use a quartz oscillator, which is the ones that are used in the clocks and watches. And then you can use things like GPS or atomic sources. You can use there's many ways of getting a signal, but the whole point of a clock is something that oscillates at a given period. And the period doesn't have to be the same. You can decide what the period is if it's a period that you want. If you want a clock source every time you feel like you're hungry, so you wait until you're hungry and then you press a button or you set some sort of signal and then or you flip a switch. That will give you, that will also give you a clock signal if you want. Okay, so clock sources are those, and I don't know how I did that, but my word, come on, this, yeah. So what is the next thing that we're looking at? We know you can get clock sources from wherever. You can build as you want and get a clock source from wherever. And then there's elements of good design. You shouldn't have more than one clock if you want to have a stable design. Try always to have one clock and use that clock and use it in various places in your design. And then the other thing is try and always use the rising edge, but if you want to use the falling edge, you can always use the falling edge as well. And then let's look at this. So clock, poor design. Let's actually look at them. So this one is always a positive edge clock divider asynchronously set that. And then always a positive edge clock divider 2, which is being set up here. Then have this set. So what is happening here? There's something that is being implied here, because this one is based on a reset, and this one is not based on a reset. And then as well, this is also being oscillated. There's implied largeness, and this document is somewhere here. Where is it? Listen to latches, implied latches, blocking, latches. So here's the thing. Latches, non-blocking, blocking. Don't do this. So the result in simulation is simulation dependent. So if you do this, this is like you're doing a blocking assignment, and then this is a non-blocking assignment that is depending on a blocking assignment. Hardware might do this differently than oscillation might do it, so don't do it. What I wanted to see somewhere else, there was a simpler sort of explanation at some point. But the whole point is that blocking assignments and non-blocking assignments, we should avoid latches completely, because latches will cause, yeah, look at it. This is called a latch. It requires memory. What is happening here? There's an input IS, there's an input IV, and then there's an output register output register OR. We're saying if IS is set, then OR is equal to IV, and this is blocking. What is happening here is that this is dependent. This is a blocking set, number one. So it will wait here. This is a blocking set. It will wait here. And the other thing is we need to know what IS is. It's implied in this instance. It's implied, but we don't know what it is. So it could be some random thing, But then you end up with a subtle timing error. Then you end up with something that you can't read. It works in simulation. It might seem like it works. It doesn't work. And then in hardware, it does something completely different. It's like, remember what we talked about yesterday. It's very, very difficult to debug hardware. So you want something that you can debug in simulation, and you want to follow these little best practices that end up giving you the sort of thing that you need, so that you don't end up making a problem. Okay, so basically what we're doing here is what is being said in both of the things is to avoid inferred latching. Avoid inferred latching. Always do explicit sets, and then use those explicit sets while you're doing your settings and your assigns and your de-assigns. Yeah, de-assigns is an actual thing. So don't use implied latches. If you're gonna use a latch, actually set it so that it's actually I'd like to put that back where it was. I would like to, you want to set it explicitly, then use the assign large, and then these are all basically being oscillated based on the beginning clock. And here the beginning clock has an implied large, and here it doesn't have an implied large or an inferred large, and then that is basically what makes a bad design. Next thing, so what does the reset state mean? It's very easy to look at when you're looking at a D flop, D flip flop, D flip flop, flip flop. If anyone has any questions, you feel free to ask them, please. Yeah. So a flip-flop is an electronic device that is used to be precise, a kind of memory component that can hold one bit of data. A flip-flop has two states, a set and a reset, and these states are represented with a binary or 0 or 1. So what is really being said here is that you can have a reset signal, and if this reset signal is asserted, which we'll look at, which is actually the next place we're going to look. So this video actually introduces this topic in a nice way. But let's quickly jump down. And the reset basically means an external signal that tells us to start afresh. Reset. Clear your desk and start again. Okay? Reset. Clear your desk and start again. And this is page 3 of 17 to which one? Page 3 to 17 of this one. This is lessons 2. So page 3 to 17 of here. Page 3 to 17. So page 3. This one, registers all the way to 17. And registers are basically things. Registers can hold memory, and wires cannot hold memory. But look at that presentation and you shall have this, and verilog basics and open discussion. So we've been doing the open discussion all through, because this is not my material. This is material I'm learning from, and all I'm doing is taking you through it in the hope that I will remember it. This video presents a really good concept on clocks and assignments, and which is something that we will learn when we do the practicals. But then the tasks here become that we need to implement a 4-bit binary counter. So let's look at a 4-bit binary counter and how it works, and then we can stop there and actually see, because we've already looked at a binary counter here. This was a 1, 2, 3, 4, 5, 6 binary counter. So look at it here. We have some sort of clock signal that is coming in at a certain stable rate. And at this clock signal, what we want to do is, for every one of these clock signals, we want to remember what we're doing here. We're adding 1. Every time we're adding 1 into this thing. So for every time this clock flips here, we want to add 1 into this 4-bit thing, which is 0, 0. It starts out at 0, 0, 0, and we want to reset. We want to reset it all when it gets to 1, 1, 1. Okay, so every time, the first thing we do is we apply a reset. All the 4-bit value starts in unknowns, which is x's. And if we do our tests without doing sets, if we do our tests without doing sets, which we will get to, you will see that if we do not set a value, it is known as an x in the first instant. So we pull a reset, and then the reset sets everything here to 0, and then now we start incrementing. Okay, so this is LSB, this is the LSB, and this is the MSB. Okay, so whenever the clock pulses, this is set to 1, this is set to 0, this is set to 0, this is set to 0. Okay, let's try and be neat here. Yeah, let's actually use that. For 0, let's use a dot, and this is also a dot. Okay, and then the next pulse, this is set to 0, and then this is set to 1, and then this is set to 0, and then no, I don't want this. I actually want zeros. can I do letters? Okay, so this is set to, let's click it, do that. This is set to 1, I mean 1, and then here this one is set to wait, no, I just want to draw. What's the easiest way? Let's just draw it. So this is set to 1. I can make this really huge so that we actually end up seeing it nice, and then it becomes really easy to draw on. So whenever the clock pulses, let's see what is being set. So let's pick this. This is set as 1. This is set as 0. This is set as 0. This is set as 0. And then we increment the thing. We increment this thing, so this one rolls over to 0, this one becomes 1, this one becomes 0, this one becomes 0. The next time the clock is set, this one stays 1, this one stays 1, this one stays 0, this one stays 0. And then the next time the clock sets up, so this one is rolled over, this one is rolled over here, this one becomes 1, this one stays 0, this one becomes 0, and then this one is 1. Okay? And then the next time the pulse goes, this one becomes 1, this one stays 0, and then this one becomes 1, and then this one stays 0. No, this is 0 here. Okay. And then this one's 1. This one confused us here as well, remember? So I clearly have a problem going to 4 from 3. Okay, and then this one becomes 1, and then this one is also 0 here. And then the next time it goes, this one goes to 0, this one rolls over to 1, this one rolls over to 1, this one stays in 1, this one stays in 0. Next time, this one stays 1, this one goes 1, this one goes 1, this one stays 0. Okay, next clock, what happens? This one is set to 1 because it rolls over, this one goes to 0, this one goes to 0, this one goes to 0. It all carries all the way through here. The next one, this one is 1, this one is 0, this one is 0, this one is 1. And then the next clock, what happens? So this one is, what happens here? What happens here? The next one, what happens here is that this one rolls over to 0, this one becomes 1, this one stays 0, this one stays 1. And then what happens the next one? This one goes 1, this one goes 1, and then this one stays 0, and then this one stays 1. And then what happens the next one? It's a 0, and then it's a 0, and then this one rolls over to 1, and then it's a 1. So, and then what happens here? It becomes a 1, and then this one stays 0, this one stays a 1, and then this one stays a 1. And then what happens here? This one stays a 0, and then it goes a 1, and a 1, and a 1. There you go. So this is what is happening every clock cycle. Every time there's a clock, this is what happens. This happens, and then 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 this happens. All of this happens with clock iterations. Whenever the clock pulses, we get that. On the positive edge, we do that. On the positive edge, we do that. On the positive edge, we do that. Whenever we add 1 in a binary counter, it goes over and goes over and goes over. And the thing this circuit is telling, the thing this circuit is doing, what this circuit is doing is that it's picking some bits, and it's telling the computer to go like, whenever say this and this are set, please put it on. So let's go. Not here. This one not here, because it's so cool. No, it won't light here. This one not here, it won't light here. And then we go like this one and this one, yeah, it will light. This one and this one, yes, it will light. This one and this one, it won't light. This one and this one, it won't light. This one and this one, it will light. You see? And this is how we're doing. We have a central heartbeat. We have a central heartbeat. Where's the selector? We have a central heartbeat, and this central heartbeat is allowing us. Is basically. Group selection. Group selection. So basically, as we're going through this thing, our computer is using this heartbeat over here. Our computer is using this heartbeat over here. Our computer is using this heartbeat over here. This heartbeat over here. This is a heartbeat. And it's using it to synchronize this data. Okay? So this data is tied to this computer. That is what a clock is. This is what a clock does. And so what we're gonna do is, the next time we meet up, we're gonna start working on this challenge, which is going to be building a binary counter, building a 4-bit binary counter that basically we can see if we can make it count up, we can see if we can make it count down, and then we can also can we make it stop at a particular point and try and make it count in negative edges, and all of this experiments, and we can see what will happen. And we won't use an EDA playground. We will write actual verilog, and we might also it might also be nice if we end up writing a test bench for this as well. So thank you so much. That has been me, Zach, presenting clocks in digital logic, and what clocks are, what clocks are used for, and they're associated with the other circuits and the reset signals in a circuit. Thank you so much for showing up. Thank you so much for coming. As always, be daring, learn something, try something hard, and see how far you can get. Thank you so much, and cheers. See you all